All right. So I want to comment a bit on the role of hypotheses in the natural deduction system that Billy has introduced. I don't need the rest of the system, so the system I'm going to discuss today only contains implication, and the only rules you need are the introduction and elimination rules for the implication. So I'll just write those here. So the introduction rule says if you have a hypothesis A and using that you can prove B, then by discharging the hypothesis, which is a kind of thing you do in time, you label it with some index, say 1, and you label the copy of A, or copies, as I'll discuss in a moment, with the same index, and thereby discharge it, and that is a proof of A implies B. And you eliminate an occurrence of the implication by using it in modus ponens. So from a proof of A and a proof of A implies B, you can obtain a proof of B. Whenever I say proof, I intend to say deduction, because that's the terminology for a proof in this system, but I'll probably slip up. I'll try and say deduction, not that there is much of a distinction when we're only discussing one system. Okay, before we get into the details of how this discharging process works, I want to maybe contextualize these rules by explaining, well, why these rules? Why do we accept these rules? What is the reasoning behind the form of these rules? Because without a little bit of discussion about that, it's impossible to really have an opinion about what discharging means or what these indices are really doing, and I do want to have such opinions. So the perhaps most important observation in the history of logic is the distinction between proving something in a hypothesis and proving an implication. And this distinction is hard to sort of, it seems non-obvious when you learn logic, and it's perhaps why it took so long to really become a clear feature of logic, because the argument that you see in the left-hand side here, the introduction rule, so the role of A as a hypothesis is a kind of a thing that we're presuming in the construction of B. What is that? I mean, you can imagine sort of stepping into a separated universe where A holds, and then you do something, and at the end you produce B. And what the introduction rule is doing is it's kind of taking that construction you performed in this box. Let me do it in purple. So inside this box, A is just true, right? This is a parallel universe where A holds. And then you construct B, and you kind of bring it back into the original universe with this introduction rule. That's one way of thinking about it. Okay. So some details about how the discharging of hypotheses works here. The proof above the line, so up here, deduction above the line, need not actually contain A as a hypothesis. It may not refer to A at all. So when you're discharging hypotheses, in fact, you can discharge nothing. Now that might seem strange, and it implies, for example, that from a proof of B, if you can prove B, you can prove A implies B for any A. But that does make sense, actually, right? So this is a rule which is known as weakening in the sequent calculus. I don't know explicitly, Billy, whether you intended this to be part of your system, but it's something that isn't clear unless you specify whether discharging an empty set is possible. So when you go to discharge a hypothesis A, sorry, go on.
I wouldn't actually call this weakening, because like weakening doesn't involve a use of the implication connective. And I don't think that implication is like parallel to the turnstile in sequent calculus. Yes, I would say that weakening is implicit in the in when you define what a proof of a proposition from some collection of premises is. So like that when you say like the it is a proof of this conclusion from these premises if all of the undischarged assumptions are in the set of premises. So like you can have a larger set of premises.
I see.
Um,
Yeah, that makes sense.
yeah.
Okay, so discharging can make use of none or one or more than one copy of A. So I'll give you some examples in a moment.
Oh yeah, and I think I did make this clear. It's actually etched in stone over here.
Good. Let me get the camera over there. How is it made clear? Oh, 0 or more. Oh, very good. Okay, yeah, I missed that when I came in earlier. Good. I didn't catch you on that then. Okay, so here's a proof on hypothesis A of A. It's just the A that sits there by itself. It has undischarged hypotheses, though. I'm not sure whether, so in the terminology you were using earlier, Billy, is it a deduction if it still has undischarged hypotheses, or was there a special name for that? Okay, so one might call it a deduction only if all hypotheses have been discharged by the end. This has one undischarged hypothesis A. I'm noticing the green is not very legible. I'll change to another color. So that's, in any case, an example of a deduction. Here's an example of a proof that actually uses its hypothesis. So from A, which is a proof of A on hypothesis A, we can deduce by discharge a proof of A implies A. Okay, so that is actually a deduction because it has discharged all its hypotheses. Here's a more interesting example. So I'll start with the proof I just gave. I'll discharge this hypothesis. And then I'll suppose given some other proof of A, call it pi, and then I'll use the elimination rule to get a deduction of A. So if pi is a deduction, that is, if it does not contain any undischarged hypotheses, then this is a deduction of A. Now this deduction contains what's called a detour. It's a detour because this application of modus ponens is sort of pointless, right? You start with the deduction of A, and then you use a proof of A implies A to deduce A from that proof of A. Now that application of modus ponens, you might as well have just not done it. It didn't really buy you anything, so to speak. So it's redundant, and it's termed a detour in the natural deduction literature. Okay, so I'll continue the examples on the second board. Is that blue okay?
Yeah, the blue is good.
Seems better than the green to me, yeah. Okay, so here's another example. So in this case, I'm going to show two discharges of two distinct hypotheses, and therefore two indices. So here are the hypotheses. I'm going to use modus ponens, the elimination rule for the implication, to deduce A from that. And then, as before, I'll get a proof of A implies A. Now, to use this introduction rule, I have to discharge one hypothesis, A, and, well, there it is, so I'll discharge it. And in the final step, I'm going to introduce A implies A by discharging the hypothesis A implies A. I'll make some more remarks on this, but the first remark to make is that we could have done these introductions in a different order. So we could have instead proven A implies A implies A implies A. And this fact that these can be interchanged, I mean, these formulas are not the same, but the proofs are in some sense the same. They correspond under a bijection, which is sort of to do with the role of Cartesian product or conjunction from some categorical point of view. Okay, but the thing I want to focus on for the moment is the role of the indices here that label the hypotheses. We can cook up more complicated variations of this form. So this actually turns out to be the church numeral 1 under the Curry-Howard correspondence.
Number 4 here, it doesn't have any detours, right? This is a normalized proof, right? Also, I noticed we could have proven 4 in the style of 2, right? Like, if you take 2 and replace A with A implies A, we can
Yes,
also get a similar thing.
Yeah,
And these are different.
Yeah, good point. These should be the same proof, I think.
Oh, really?
I think this is Ada expansion. Yeah, that's a good question. Let's come back to that. Is 2, or the variant of 2, this, let's say, how should I say this? 2 for A implies A. So Billy's point is that if you went back and just introduced a hypothesis A implies, well, maybe I'll put it over here. So consider the following alternate version, which gives also a proof of the same formula. We could do A implies A. From that, deduce so this is a proof of A implies A from hypothesis A implies A. So by the same argument as was used in 2, we can use it to produce a proof of A implies A implies A implies A. Okay, so then you can ask, are these the same proof?
And to be clear, we don't like literally mean are they the same proof, because they literally aren't. But
very good, yeah.
It's more like, is there some sensible notion of equivalence between these?
Exactly, yeah. So what we mean by a deduction is something we haven't really examined, right? So, well, we know, like, on its face what a deduction is. It's a certain tree of deduction rules and these discharges that is valid, but there are certain changes we might make that on reflection we would think don't change the identity of the proof. For example, if I were to change this 2 to a 3, it's literally a different thing on the page, but is it a different deduction? Well, to be careful, you might say, yes, it's different, and leave it at that, right? If there's any even trivial change, you might declare that to be a different deduction. Fine. But then there's some other notion of the same, which appears interesting, which includes being able to rename the indices that you give to discharges, but also perhaps less trivial changes. And the question is, well, does that reasonable right notion of sameness or identity for deductions, does it include this? Are these two deductions in some sense supposed to be the same? This is actually a bit more subtle than the notion. This question of when the two deductions are the same is exactly what I want to speak about, so it's very on topic, this question. But this notion of equality between these two deductions is a bit more subtle even than the one I'm going to cover. So this is related to what's called in the literature on lambda calculus eta expansion. So indeed, probably, I think you should think of these as the same, but this is maybe slightly more controversial than the things I'm going to talk about.
Can I just add something? I think so like one perspective, like the way I said it before is like, is there a sensible notion of equivalence between these two things? Is like that sort of perspective is still sort of viewing them as distinct things, but just sort of deciding on a sensible way to group them together. Whereas another way to look at it would be that you believe in something underneath natural deduction, that natural deduction proofs are like naming. So like in the sense that like 1 + 1 and 2 are the same thing. Like you either view that as like I'm sort of deciding a way of grouping together like ways of referring to numbers like 1 + 1 or like 2, versus like there is an actual concept, there's an object underneath that like 1 + 1 and 2 are different ways of naming. So like is that are you chasing that in any sense? Like
oh, exactly. I mean the definition of a sort of grouping or equivalence relation is just a formalization of that idea that the natural deduction is kind of denoting something more fundamental. We just don't have any way of accessing it more directly. But that's the intended reading. Yeah, that's right. This is a kind of recurring topic in proof theory, is our proof objects, when we write them down, seem to contain various bureaucratic elements, for example, these indices. Now you can try and dismiss that bureaucracy in various ways. You can come up with a canonical indexing, right, where like you always call the first thing you discharge 1, and other such conventions, so De Bruijn indices, something like that. But that's also not quite satisfactory, because who is the bureaucrat in heaven that gets to decide what is like the correct canonical way? Clearly there isn't such a decision. So then you allow different ways maybe, but then you should decide which ways are the same. And
you could also like literally just draw lines between the deduction rule and the discharged premises.
That's what proof nets are. That's exactly right. So that's perhaps one of the most recent attempts to dismiss this bureaucracy, is to make it geometric in some sense by drawing lines to connect where hypotheses are introduced to where they're discharged. That's exactly what proof nets do. Almost successfully, but then still I think this story isn't over. So yeah, it's a very interesting the quest for these things that proofs are denoting. What is the true identity of those things? Arguably natural deduction is, or proof nets are closer to that thing than many other systems. But yeah, this is an active sort of area of debate, if not research. Okay, so I said this was the church numeral 1, or corresponds to the church numeral 1 under Curry-Howard. I haven't said what the church numeral 1 is, but maybe you know. So let me say what the church numeral 2 is, as a way of giving a more complicated example of these discharging of hypotheses. So here goes. So it makes use of the same elements, the same tricks, right? So here's the elimination rule for implication, applied once, and then we can apply it again. So this is a kind of strange way of proving A. We have two kind of pointless seeming roles for A implies A. And then we can discharge the A. So that's one. And then we can discharge, well, we get to choose, right? We could now, so I'm about to prove this. Okay, so the proof up to here is a proof of A implies A on, well, this hypothesis has been discharged, so there's two open undischarged hypotheses. Now, I'm going to put in an introduction rule, which from the proof of A implies A on the two hypotheses, which are also A implies A, we'll get a proof of A implies A implies A implies A. But I can discharge one, none, or both of those hypotheses. If I want to immediately be finished, that is, have a deduction with no undischarged hypotheses, well, then I should do both. And I will. But I'll come back to the case in which I only discharge one of them in a moment. Okay, so this deduction is the church numeral 2, and I'm just going to refer to it as the church numeral 2. It corresponds to the church numeral 2 under the Curry-Howard correspondence. Okay. Well, so here's the interesting question. I just produced for you two proofs of this formula. Now, logic historically has largely concerned itself with provability, right? So if you have a proof, then that's it, and maybe there's more than one, but who cares? In which case, whether or not two proofs should count as the same is kind of not an interesting question. It's out of scope, if that's what you think logic is about. But nobody stops me from asking this question, right? Should I think of these two deductions as the same? And that's a kind of similar question to this one. I've kind of biased you to answering no by giving them the names 1 and 2, right? So that it would seem kind of peculiar to insist they were the same. They're not literally the same. They're different chains of reasoning. They involve different numbers of rules and used in a different way. But they are in some deeper sense different. They have a different structure. But, well, what is that structure? On what grounds am I supposed to reject the idea that these are the same? So that's something I want to get into. Looking at them, one sense in which they're clearly different is the pattern of the way that hypotheses are used is different, right? So in the proof in 4, there's only one copy of the hypothesis A implies A that's discharged in the final step, whereas in the second proof, in part 5, there are 2. So this seems like the most obvious difference, and it is indeed why one is called 1 underline and the other is called 2 underline. Okay. So I want to dwell for a moment on the role of the numbers 1 and 2 as indices here. So I'm going to move over to the third board in order to do that. Okay, well, the question of whether these two proofs are the same seems subtle, but we can agree, I think, as I said earlier, that if I was to simply rename the things I'm using to denote the discharges, say from 1 to X and 2 to F, you would hardly object to the idea that those two deductions are the same, I hope. Or maybe not, maybe the same is kind of too vague. Let's say contain the same logical content, or express the same idea, or the same deduction, or the same relationship between the hypotheses and the conclusion. Some mix of all of those. So I'll just quickly reproduce the tree. All I'm going to change here is the letters that I'm using. So I'll write F instead of 2. And X instead of 1. Okay, is this the same as 2? Oh, probably yes. But then this raises a broader question of, well, what are the rules on these symbols 1, 2, X, F, etc.? I mean, exactly. We sort of know, it's intuitive the way you're supposed to use them, but what are the exact rules? Okay, so let me be more specific. By giving you an example that kind of maybe you think it's obvious what the rules are, so let me disabuse you of that, or try to. So I'm going to use these symbols in a way that hopefully you'll think is wrong. And then you have to tell me why it's wrong. Okay, so in the first step I'm just going to do the same thing I did before. I'm going to stick with the letter X, because why not? I'll discharge that hypothesis to get A implies A. Now I'm going to discharge one of those hypotheses. Nobody stops me from just discharging one. I'll call it F. Let's say this one. But I left the other one, and now I'm going to discharge that one. But I'm going to call it F as well, because you didn't stop me. But clearly there's something wrong with that, and maybe one way of saying it is there's more information in the recording of this, of me literally presenting this deduction, the video file, than on the board. And that extra information is exactly the fact that in the process, when I was writing from top to bottom, I wrote this F first and then this F second. Okay, so what's your answer to that, Billy? What's the rule here that I'm violating?
I guess two distinct inference rules need to use distinct indices.
Yeah, so I think there's kind of two things that need to be remarked here about why this is wrong. The first is to make very clear that maybe I want some name for these. So let me call them names. Okay, because there's nothing else in the system that has the label names. The formulas are things like A and A implies A, and let me just only use the word names to refer to these indices that are used in discharges. Okay, so names, the first maybe point to say is that names are introduced at I rules. This is implicit, and Billy's been pretty clear about this, but it's quite different from, for example, if you were to see a typing tree for a lambda term or a sequent calculus deduction, where you introduce these names or something very similar to them at the point where the formula is introduced in an axiom rule or as a hypothesis. So we could have a system of natural deduction that looks like that, right? You could say something like, okay, I'll introduce A, and whenever that's discharged, I'm going to use the letter X to stand for that. And then when you get down to actually use it, you just refer to that copy. And then if you wanted to eliminate multiple ones, then you'd have to maybe, put X, Y, Z or something there, right, to say which hypotheses you're going to use. But that's not the system. I mean, you can make a system of natural deduction that way, but that's not the way that Billy's presented it. It's not the way I'm intending it to be read either. These names, the F's and the X's, they get invented at the moment of this introduction rule, and then they get stuck onto the hypotheses as appropriate. Right? So there's something that is introduced at the moment of that rule. Okay, so, and if that's clear, then we can add the rule that Billy just mentioned, which is distinct introduction rules use distinct names. Or to put it slightly differently, you never reuse a name that's already appeared earlier in the deduction. Okay. So maybe I can fix this then. Let's see, do I want to do it on a different board? Yeah, maybe I will. Okay, so let me write down a correct version of this deduction back on board 1. Correct in the sense that it is still a deduction, has more or less the same form, but actually follows this rule. Okay, so here's a fixed version. And pay attention to how this evolves in time, right? Because this evolution in time is sort of present, given the convention that was in the first bullet point that I just made. Okay, so A implies A, 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 A implies A, A. Alright, so this X now appears. So I shouldn't reuse X, maybe for a different reason, but in any case, that was never a temptation I had. So we'll call that F, and we'll call the other one G.
Actually, on that point, I wasn't sure if it was sort of relevant to the content of this talk, but there is some sort of understanding that these formulas we're using like are kind of a free structure in the sense that there's no it wasn't even up for consideration that A implies A could be the same formula as A. So you can't like discharge two like cosmetically different formulas because they're literally always different.
Yeah, that is important. Okay, so that's fixed. This actually corresponds to the, maybe I shouldn't call it Church anything. I don't know that Church or his students ever worked on this, but under the Curry-Howard correspondence, this corresponds to what's called a binary integer. it's either 0, 1 or 1, 0, depending on your convention. So this is not a stupid deduction. This is as interesting as the church numerals are. Okay, so what's important here, well, it's not the letters X, F, and G, it's the pattern of their occurrence, right? I could just replace this completely by colors if I wanted to. It's the fact that certain appearances are linked, and that the symbols tell you which hypothesis is being used at any given point. And maybe you don't have to use every occurrence of a given formula, which is a hypothesis, at any given moment. I haven't convinced you that you should be interested in the distinction between this and the alternative one, right? So here is another proof of the same formula, which we could ask this recurring question about. Should these be considered as the same or not? I'm not proposing an answer to that question, but at least want to make clear that there are enough proofs around that it isn't obvious that, first of all, there's only... Well, I want to dispel the idea that there's only ever one proof of a formula, and to make this question of whether they should be counted as the same or not seem like maybe it doesn't have an obvious answer, or at least the answer isn't obviously yes, they're all the same. Okay, so here this gets discharged at the same time as before, but this, let me call it G now. No. Okay. This would be stupid. This would be the same, I think, right?
Yeah.
So that's not what I wanted to do. I wanted to keep the letters on the discharges the same, but say, okay, at this first step, I'm not going to discharge the hypothesis I just discharged before, but the other one. Okay, so question, are these the same? I mean, the pattern of usage of hypotheses is different. So if that matters, then the answer should be no. Okay, so I want to set up... I'm going to just state the Curry-Howard correspondence. It's not... won't be a precise statement, but I want to have at least enough discussion on the role of hypotheses and when using them counts or doesn't count as the same, so that that statement has some content. So let me just be sure about that. Okay, so here's maybe a question to ask. How do we know what undischarged hypotheses are available at any given stage of the deduction? Right, if you think of the deduction as a performance, I get up to some stage in the deduction, let's say, I get up to here, then what am I allowed to do? So when I'm up to that point there, this hasn't been discharged yet. And if I'm going to do an introduction rule, I have to discharge something. And, well, what can I discharge? Well, clearly you sort of have in mind the idea that I'm going to look up the tree and I'm going to look into the branches all the way until things that are hypotheses, and then anything that's been discharged at some earlier introduction rule I'm going to forget about. So that gets rid of those. And then, well, up here there's something that hasn't been discharged yet, and the fact that hasn't been discharged yet is even meaningful is kind of based on your belief that you can formulate a clear definition of that, making use of the structure of the tree, right? The idea that the available things, let's dig into that a little bit. How do you know what's been discharged or not? Well, you have a principle that says that these rules don't change it. They don't change availability, let me just put it that way, right? They don't change that if a hypothesis is available to be discharged, then somehow that availability flows through elimination rules unchanged. And you have a sort of idea in your head, hopefully, that this introduction rule, it removes availability, but only for the sort of copy that is actually named or denoted by that symbol that's the index, right? That picks out certain available hypotheses to be removed from the pool. Okay, but let's be a little more clear about, we have to, the available hypotheses for discharge are a set. They don't really come with an order, at least the order doesn't matter to us in deciding what's available or not, but not a set of formulas. Okay, I mean, it's kind of a set of formulas with their locations, right? To be clear, if it was a set of formulas, that would mean that, let me now mess up the second copy, if the available hypotheses was just a set of formulas, then what would be available here at this moment of this deduction? Well, it
Just
would
A
be,
implies A.
it would just be A implies A, right? But then the second introduction rule here would be nonsense, because if the set of available hypotheses was just a set of formulas, not formulas with location, then this introduction rule would eliminate both at once, because it just removes A implies A from the set of formulas that are available to be discharged. So that isn't what we mean, or at least I say it isn't what we should mean, because it forbids you from actually forming the proof that I have, both of the proofs that I have here. And there are good reasons for thinking that both proofs should exist and should be distinguished. Those reasons are sort of outside of natural deduction itself, which is, often where reasons for things come from. It's from the connection to lambda calculus, which is the Curry-Howard correspondence. Under that connection, it seems very natural, actually, to allow both of these proofs, and therefore to have the opinion that the available hypothesis is not just a set of formulas. Okay, so what is it? I've given the answer. You should think about it as a set of formulas with location. Let's just say located formulas. So formulas together with a position in the tree. Okay, so I think that's not completely formal, but hopefully clear what it means for how to determine what the available hypotheses are in any natural deduction, at least with only these two rules. It doesn't change as you flow down the tree through elimination rules, and it changes in the way I've prescribed as you flow down through introduction rules. Are there any questions about that before I state the theorem?
I like the way this idea of a located formula will be some kind of like formula with some tag associated to it or some identifier that's distinct from other things. Is that what you have in mind?
Yeah, that's right. Or just the structure of the deduction itself as a tree. That mathematical structure, I mean, you could think about representing it kind of as a data structure in various ways, but if you think about it as kind of the elimination rules introduce two branches, so you could kind of think about that as pairs of natural deductions and sort of structured as pairs of pairs, or
Yeah.
and then you would specify the location by giving a binary string, left, right, something like that. But the precise form of that, I mean, I could give you a formalization, but its content doesn't really matter, right? As long as you have some way of determining it, I think there's no confusion possible there. Okay, so I'm over on the second board now. Let me just sort of vaguely state the Curry-Howard correspondence. And then I'll throw a bit more confusion into the mix by pointing out how the convention for how we thought about discharging actually doesn't survive if you want to generalize this even slightly. Okay, so the Curry-Howard correspondence says that simply typed lambda terms, and I'm not going to define those. So those are terms in the kind of prototypical functional programming language, which only has lambda abstraction and no other basic term formation operations, like no pairs, so no sum types, nothing like that, just lambda terms, which are closed. So that is no free variables. So that is everything. Every variable is sort of is bound by some lambda, and take them up to alpha equivalence. So alpha equivalence is exactly what corresponds to the belief that if I discharge things by naming them 1, it's the same as discharging them by naming them x, and the precise symbol doesn't matter. That's literally what alpha equivalence is. Are in bijection with natural deductions. Up to the renaming of, renaming of names, that's redundant, so I'll just say renaming, and just remind you, so that's like x for 1 and f for 2, introduced above.
By natural deductions here, you mean like your definition of deduction, which has no undischarged hypotheses?
That's right, yeah, thanks. I should have. And as I guess is clear, only with the introduction and elimination rule I specified. Yeah, let's just be, so with no undischarged hypotheses. And the process of making clear to ourselves what it means, what the list of undischarged hypotheses means, and how you manage that actually is the proof, properly understood. So we don't really have time to get into the proof now, but you've kind of seen the idea. Now, I gave you some examples already. Well, the second one I put on the previous board was 1, 0. So the order of the discharges was different in the two natural deductions, and that corresponds to the binary integers 0, 1 and 1, 0, respectively. So maybe I can write out lambda terms quickly. So one of these corresponds to, I forget which one. Let's have a look on the... So the top one, I think... So I called this one, which one did I call 0, 1? The top one, which discharged the G last, so that means the lambda G is on the outside. So something like lambda G, lambda F, lambda X, and then I should apply, I've kind of erased which one was which. But I think the top one, the G corresponded to the lower copy of A implies A. So that should be G applied to F applied to X. And this is lambda F, lambda G. Oh, I did the same thing. I'll do the... Okay, so those are the lambda terms corresponding. Well, why invoke the Curry-Howard correspondence if I'm not going to prove it? For two reasons. One is to give you some evidence that the distinction between things like 1 and 2. So remember, these were proofs of the same formula, and these two were proofs of the same formula, but a different formula to that which 1 and 2 were proofs of. It's some evidence that you might care about distinct deductions or proofs of a single formula. They have different computational content. That's because they manage their hypotheses and invoke them in a different pattern. That's just another way of saying the same thing. Okay, and introducing this allows me to make the following two remarks about how we think about discharging hypotheses. I'm looking at the wrong board here. The first is that introducing names, well, maybe given the time I'll just make the more important remark and leave the other one. There's some notes I'll post to the Discord. Okay, so it's important that on one side you have lambda terms or programs which are closed, and on the other side you have deductions with no undischarged hypotheses. It's only true in, well, that's the statement. If you want to have lambda terms which do not close, that is, they have open, they have free variables in them, to correspond to deductions which have undischarged hypotheses, well, clearly then you're going to have to do something like give names to hypotheses before they get used. So if you want to correspond to deductions with undischarged hypotheses, so an open term would be something like lambda x, f applied to x. So f is free here. And a deduction with undischarged hypotheses, we've seen several examples of that already. But if you're going to take such a deduction and correspond to a term, well, you need to name everything in your lambda terms. So the undischarged hypotheses will need to get names. So that's the sort of contrasting convention that I mentioned earlier, where as soon as you introduce a hypothesis A, you introduce also a name for it, which is then referred to later if you discharge it. So the introduction of names at the same time as hypotheses is necessary if you want to, well, name them and give a corresponding term. Fine.
And then the name of the hypothesis is different to like its identity as a formula occurrence, because you might want to name two different formula occurrences with the same name.
Exactly.
Right.
So that brings up a whole kettle of fish, right? So you might, okay, are names distinct then? That is, right, is a located formula, do they all have distinct names? If not, how do we discharge them at the same time? Right, if you were to give, if there were two A's floating around and they were sort of, maybe I'll switch to a different color for this new convention on names. So these are introduced at the moment of birth of the formulas. If that was to happen and then later on you want to discharge both of them, as we did in the church numeral 2, right? So that is something we want to be able to do. Should you name both of them at that moment? That seems like a reasonable thing you might do. Or you could just allow yourself to give them the same name when they're introduced and just use that name. So both would be potential choices. Okay, so, there's other things that of a similar nature that you might ask about. But the conclusion is that this policy of naming hypotheses at use that is, at the time of the implication rule, cannot survive, in the sense that you you can't continue to do that and extend the Curry-Howard correspondence to open terms, which you don't have to do, right? You could take the attitude that, well, any term that's open, for example, this one here, I can always close it by sticking a lambda abstraction at the front. And then that is subject to the ordinary Curry-Howard correspondence, no problem. And similarly, if I have natural deductions with undischarged hypotheses, at the bottom I can just discharge all the hypotheses, right? Which corresponds exactly to just closing off the term. There are reasons to not think that's the kind of most elegant resolution to the story. Maybe that's for a different time. But I do, I guess, want to have as the takeaway for this session, I want you to have the idea that logic is not a self-contained system, right? The question, well, what is the right policy for dealing with hypotheses? Should you name them at use, or should you name them when they're introduced? These choices sometimes in logic seem to happen in a vacuum where it's just a matter of taste, right? And I suppose you could take a very kind of isolationist point of view and say that that's perfectly fine. A more mathematical point of view might be something like, well, when you take that system, logic viewed as a mathematical system, say natural deduction in this case, when you place it next to other similar systems, what does that choice mean? What does it correspond to? And in that different system, maybe there's some choices that seem more natural or not, or at least you might learn something about the nature of the choices that you were making in the original system. And some may start to seem more artificial than others. And that's often the way in which connections between logic and other subjects, in this case computer science, it's often the way in which they inform logic by making otherwise ad hoc decisions seem to carry different valence because of the way that they correspond to different choices in the other system. And this management of hypotheses seems perhaps, when you first see natural deduction, as, well, who cares? It doesn't change what I think is true, so it's not important. But when you view natural deduction from a computational perspective, this management of hypotheses is everything. This is what the subject of lambda calculus is about. So it no longer appears to be the kind of bureaucratic thing that it may otherwise appear to be. Okay, so that's all I have to say. Are there any questions or discussion?